Welcome back, everybody. We're going to continue with the translational science session. It will be chaired again by myself. I'm Ben Forbes from King's College London, with my colleague.
Regina Schellies from Kiel University in Germany.
Okay, and so I'd like to welcome our first speaker to the stage. So the first talk will be by Catherine Fromen. Catherine is an assistant professor at the Department of Chemical and Biomolecular Engineering at the University of Delaware. She has a PhD in chemical engineering from North Carolina State University. She's performed postdoctoral studies at the University of Michigan, and her area of expertise is inhalable immune modulatory formulations and the development of experimental dynamic full volume approximations of the airways. So what we're going to hear today is about a model for spatial deposition. Catherine, over to you.
Awesome. Thank you so much for the invitation and for the introduction here, and for all of you for making it back from the coffee break. So it's my pleasure to give a talk about a preclinical model that we've been working on in my lab at the University of Delaware that we gave a fancy yet informative acronym, TIDAL, Total Inhalable Deposition in an Actuated Lung Model. And so really briefly how we came to this, I'm in the chemical engineering group. I said immune modulatory formulations, and that's really where we started, and is the focus of a lot of efforts in my group of thinking about different particle formulations that interface with the immune system. But really early on, we came to the conclusion that without thinking about models and how we could test these formulations, we were really at an impasse. And so a large effort in my group has now been focusing on developing lung models at all sorts of different length scales to think about how we can better predict immune modulatory effects in the lung. And so I don't really have to introduce this challenge to this audience, but we have really focused our efforts largely on physical models because these offer us an opportunity to ask questions that maybe we can't answer through clinical assays, and also think about validating these wonderful in silico approaches that we have that still have their own limitations too. And so in this physical model space, we're really thinking about, as many of us are, multi-scale and multi-dimensional problems of thinking about first, where do the therapeutics go in this heterogeneous lung space? Where do they fall within these kind of large length scales down to the micron scale sort of formulations? And certainly then answering the question of how well they're going to work in the lung, thinking about everything from dissolution to then immune modulatory properties. And so this really multi-dimensional, multi-scale challenge from centimeters down to microns is really where the challenges of physical models lie, right? And so we've really relied on 3D printing and these advents in additive manufacturing to think about new ways to, let's see if this will play, to think about new ways to rapidly prototype new models and assay a whole bunch of different intra and inter-patient variability. So we in our lab use a carbon 3D printer. It's just our flavor of choice here. This uses digital light synthesis, or CLIP as they've coined it. We didn't invent this technique, but essentially it's a transparent window that's oxygen permeable, allows for photopolymerization of a liquid resin on top, and we can pull out a solid part from this. And while this video is sped up, it's actually a very fast technique, so all of our prints happen under 6 hours, and we have access to a really large physical size. So we're really only limited by the build platform and then the height of that platform within this space. And so you can see my student holding a full-size adult lung model up and to the right of what we're able to access with this sort of technology. All right, so building on this, we started with making mouth-throat models and thinking about how we could assay different upper airway sorts of questions at different length scales, and so we have some work in pediatric space. We also were interested in thinking about how we could control flow at the outlet of these models to assess different heterogeneity. And in the top right, you can see that we have access to flexible materials, and so we started to push the boundary of how far could we go with these sorts of technology. And that's really where our interest has lied going forward, is thinking about the downstream airways that we can't really get immediately from these upper airway models. And so we set ourselves a pretty ambitious, and you could argue crazy goal, and these are my PhD students who've been working on this. We want to build a model that allows for entire spatial collection throughout the lung. So not just thinking about grouped regions, but really capturing the heterogeneity within the airspace at low level information. We want the full volume. We want the full spatial, the whole surface area. We want the whole kit and caboodle here. And we want to be able to assess a wide range of doses, but the full dose too. So capturing any interparticle dynamics that are really difficult to capture by maybe in silico approaches. On top of that, if this wasn't challenging, we want the breathing dynamics. We want to be able to capture the non-uniform flows that exist within the airspace. And to top it on that, we don't want a healthy person, we want it to be modular. We want to be able to adapt this to thinking about disease states going forward. So this is our approach to developing this model. We can start with what we're able to capture from patient-derived data. So if we take CT scans, we can reconstruct some aspect of the airspace down to somewhere 6, 7, 8 generation. But then we're really left to think about how we can approximate the rest of that lung airspace. And there's a lot of it. So we can think about stochastically modeling all of those tubes and bifurcations, but that becomes really challenging computationally given that dynamic length scale. And also the fact that we can't really manufacture it. So the common misnomer about additive manufacturing, it can't do everything, it hates tubes, which is what the lung is made of, right? So we need to think creatively about how we can capture the critical features, the transport properties of this porous structure without actually having to make tubes all the way down. So what do we have to maintain, and how do we want to keep the key critical features? We want to make sure we keep that upper airspace, right? We know that that is really informative on the flow of lung going down. And we can take advantage of the fact that the lung is naturally grouped into these lobe-level discretization, which allows us to have some of that hierarchical spatial distribution. All right, so this is the first part, but what goes on in the inside, right, is really critical. I said we're going to get spatial deposition throughout that airspace. We have to populate that with something. So here's our design. We start with that patient-derived upper airway. We have these 5 lobe modular units. We can plug and play with different patient-derived information. And essentially, we build each of these lobes like a trumpet model, but at the lobe level instead of the whole level of the lung. And so that's sort of shown in these concentric rings on the left here. So if you look at the lung architecture, we take those bifurcations, we can pick a typical generation, we can look at the cross-sectional area there, and that defines the diameter of the lobe inlet here. We can then define a length based on the total volume of those generations, and we can subsequently build that lobe level downward until we reach kind of the build platform limit, and we can just approximate the length longer to capture that volume. So then what's important as we go through this lobe? Well, we have to make sure that that background airflow is representative of what's occurring in the lung, but there's a lot of other features. So do we want to capture the tube diameter through some sort of porous structure? Do we want to capture the right surface area of all those generations? And this is still the open question that we've really spent a lot of time working on. The most important thing is that it provides that spatial deposition. And so what we've chosen to do is populate each of these lobes with 3D printed porous lattice structures. You can think of these as really terrible filters, and they're on huge length scales compared to what we heard about this morning. So we can make these pore sizes on the order of millimeters. This is a macroscopic part over here. I apologize for the inches. But we essentially can make these down to much smaller granulations. They're periodic, they're repeating, and they're based on a single unit cell. So we have some idea of predictability within this space, which is really important. And so I'll show you that that really tracks to deposition going forward. I also said we wanted breathing dynamics, and so how do we do that? Well, we make this all out of elastic material, we put motors on the end of it, and we actuate these. So these are sealed compartments that then allow us to have some sort of inlet and outlet deposition. And so this is our model. All these parts are interchangeable, and so we can plug them in and out. And what I'd like to do with my remaining time is just show you where we're at in quantifying breathing dynamics, spatial collection, and kind of the vision for it going forward. So we started with a small volume prototype. I mentioned we're chemical engineers, not mechanical or electrical, so this was a kind of a Herculean feat for my chemical engineering PhD student. We start with an idealized adult upper airway here, and we have these small volume lobes that have just a flexible unit at the end. So this is our idealized airway. We can discretize our right side lobes, our left side lobes, and our total volume is about 1 liter. So this is definitely smaller than a full adult. But what we can do is then measure at the mouth inlet, just like our spirometry data, and measure our airflow dynamics through this. So what I'm showing here is a plot of our time versus, our flow rate versus time of the repeated inhalation maneuvers. And so what you can see is our first exhalation followed by inhalation as we actuate synchronously all 5 of those lobes. And we can then integrate under those curves to find and overlay a normalized flow rate versus volume. And so you can see that these are very reproducible and they overlay pretty uniformly. If you're used to looking at spirometry data, this is not a forced expiratory maneuver, right? So the shape is not the same, but we're really trying to match some of the more tidal repeated movements. And as we have complete autonomy of those motors, we can really map out very different curves from that flow profile. So just showcasing things that we can do. We can control the flow rate of our model, and so just highlighting the different levels within the small volume that we can achieve here, all mapping out to the same volume exchange, so just by tuning how fast those motors go. And then we can think about doing the same by actuating different fractions of the total volume. That's all synchronous. We know that that's not true in disease, so we can think about offsetting the lobe involvement here. And so just a proof of concept, the bottom lobes completely exchange air, the top lobes exchange different fractions, and we can sync up the breathing profiles from here too. One important thing we wanted to make sure to include was to have offset breath hold, and so we know for inhalation devices this is key, and so we can readily do this in our model. So if you were looking for a video, this is just a cute display of all the things that we can do at these different size scales, and we can go through and look at involvement of individual motors, synced up motors, and show the different speeds and flow rates on this initial prototype. And so we're really excited that this allows for a pretty good establishment of the controls that we needed to establish, but also then thinking about the materials, and we learned a lot in putting this together, so our next generation materials are easier. All right, so the big question, right, is the spatial collection aspect of this, and what are those periodic porous media? And so in our full-scale model, this is thinking about grouping different generations and matching surface area. And so you can see that in these groups of generations, we can control the porosity of these 3D printed lattice structures. But we have a huge library of opportunities. And so this is really the challenge, because while these look like a filter, they're so much larger than any porous media that's really been established so far. So we had to do some of our own evaluations on the transport properties. They are porous. They do follow traditional organ-like behavior. And we're in the process of now quantifying the aerosol deposition in these lattices. And so just a visual, if we do scale the dimensions of our lattice, this is just a cubic structure. These are 1 micron aerosols under a constant 15 liter per minute flow rate. You can see there's differential deposition. And so as you scale the dimensions of these flow properties, you can see differential aerosol collection. At the same porosity, defining the unit cell geometry leads us to a huge range of deposition efficiencies, and that's really what I want to draw your attention to, is we have a wide parameter space to work with. All right, so does it work? Does it actually map to spatial deposition? So we take our single lobe small volume prototype, we populate it with 2 different lattice regions. The first one is more open, more porous. The bottom lattice 2 is a lot more fine, smaller pore sizes. We take an aerogen nebulizer and we insert a fluorescent molecule that we can track throughout the system. And we can have this breathe over a 10 breath, 40-second flow profile. Collect the exhaled fraction. We have a little switch valve here, and we can then quantify the total dose that we collect, so by washing all of these parts. We capture 91%, so total mass balance we think is pretty good, and that's pretty reproducible. And then when we look at where the aerosols are going, we lose a lot in the tubing and the nebulizer going in, but we actually do see about 61% depositing in the model and an exhaled fraction of 16%. So it's aerosols are able to go in and come out of our model, which we actually think is really representative of aerosol deposition. Within the deposited dose, where does the aerosol go? So we lose some on the wall of the model itself, but we see about 60% going in that upper airspace, 20% that gets to that second lattice and is collected there. So again, getting us a 3-to-1 ratio of these 2 different regions. And so we've done a number of these studies of different aerosol sizes, and where we're headed, and what I wish I was able to tell you is it's fully validated, but it's not. So we're working through kind of monodispersed aerosols, trying to map up initially to 2 regions, thinking about central to peripheral of monodispersed aerosols. And so looking at benchmark clinical data on the right here, we can think about how these might map to 2 regions of our lung airspace. It's not totally accurate, right? And we have to take some of our middle carina region as well. But we're in the process of doing this, and I think it's really promising in the inhalation, exhalation so far. Where are we going? We're hoping to be able to map this to disease. And so while I've shown kind of uniform 1 lattice that fits a healthy person, we have so much control from the 3D printing side of the features of this lattice. And so these could be obstructions, thickening, added resistance to a particular lobe, a particular region, to guess that some heterogeneity and also thinking about deterioration on other parts too. And certainly with that low-level motor control, we can think about offset motors and involvement of airflow at a more macroscopic level. So this is a model. It definitely has many limitations, but hopefully I've convinced you that there's a lot of opportunity in thinking about the breathing dynamics and spatial collection at a full volume, full size lobe. We're happy to follow up. I'm happy to follow up with any discussions on where you can see this fitting in this kind of specialized assessment of different aerosol formulations and opportunities to develop and benchmark going forward. So I'd like to just conclude thanking my funding, my group, my collaborators, especially Ian Woodward, who's really pioneered this and will be looking for the job in the coming year. And thank you all for your time and attention. I'd be happy to take any questions.
Thank you very much. Do we have any questions? While people are thinking, so what do you think the real sort of contribution of your model is going to be? Is it that ability to adapt it to represent disease states that you think is really where it's going to have its
Sure. Yeah, absolutely. I think that's really the benefit of it. And so having that heterogeneous airflow involvement is really critical down the road, and that's, I think, a missing piece. So it's not going to replace a cascade impactor in terms of quality control and size distribution, but then thinking about it in specialized cases, when you have a patient population that is unique, can we have a generic model that would be able to assess how the baseline interpatient variability will factor in, I think, is a real opportunity.
And just a practical question would be, how easy is it to wash and recover your aerosol from the different places?
The goal is that we can pop them into different bags, just like an NGI. Practically, it depends on what the formulation is. So I'm happy to talk about all the nuances. Lots of lessons learned so far.
Okay. Question?
Yeah, Mark Nagel, TIDAL. I'm just wondering if you're doing anything to mitigate electrostatic charge on these components.
Yeah, no, it's a great question. And everything is made out of plastic so far, so it's a huge problem that is TBD. So we've been thinking about we've been thinking about it and happy to follow up on it. Yeah.
Maybe related to that, I'm here.
Sorry. Oh, gosh.
So you showed that you have this flexible, let's say, bulb at the very end. Could you also do this mesh in a flexible manner?
Yeah, so we haven't because we also have computational models in the background to try to get to this, and so having the unsteady state flow and a moving framework was, my student yelled at me that it was not going to happen. But down the road, we can certainly make our meshes, and we have made them out of flexible materials, so we're hoping to populate the entire version in the kind of version 2 that would have aerosol, would have lattice throughout the full compartment and flexible too.
I'm actually speaking up next, and I'm talking about waveform shape, and I notice you've got sinusoidal, and of course we're 1/3, 2/3 when you're normal breathing, but actually it may get more sinusoidal with disease. So are you able to adjust that?
Yeah, absolutely, and I didn't show that here, but we have, especially in the full volume, as we have a much bigger dynamic range in how we can control that. The hemisphere shape really is critical in how we can control the speed and flow exchange there too. So we can map out, and what we're really trying to do is get to much more clinically relevant waveforms that I'll be interested to hear, and maybe we can chat on how we can reproduce that in our model too.
Okay, thank you very much, Gavin.
Thank you.